Okay, so this is from the calculus book. I didn't copy this because we really just need to look at it. We've already done this. So if we're talking about the limit of this equation as x approaches 1, remember the limit is saying what does the y value do? So as we're looking at this as x approaches 1, from the left side to this parabola, your y is getting close to 2. As x approaches 1, from the right side, your y is approaching 2. So the answer for this limit is 2. So you can do that by looking at a graph. There is a table. You can use tables to figure this out as well. If we want to see what is the limit as x approaches 1, we have 1 in the middle of the table. And then we're going to try numbers that are just under 1 and just above 1 and look and see what the y values are getting closer and closer to, which they're getting closer and closer to the number 2. And then this example here, exactly the same thing. We can look at a graph to see from the left, as x approaches 1, y is getting closer to 2. From the right, as x approaches 1, y is getting closer to 2. In this graph, compared to the other one, this graph, there's an open circle. The other one, there was a closed circle. Either way, the limit is what the y is approaching, so both of them have the same answer. And then the table is the same way. We are approaching 1 on the x's, but on the y's, it's getting closer and closer and closer to 2. It just doesn't equal 2. On this question right here, if we go from the left and we are approaching 1 for the x's, y is approaching -1. We go from the right, we're approaching 1 on the x's, y is approaching +1. If they do not match, the limit does not exist. If from the left and the right, they don't meet at the same place, the limit does not exist. And you write does not exist. And you can see that in the table as well. So those are 2 methods of finding limits. There are 3 total methods. And we've kind of started the third one. We've done a little bit of the third method as well when we were doing chapter 2. So the 3 methods for finding limits, 3 main methods. Three main methods for finding limits would be, number 1, we could graph it and look at it graphically. Or if we can have our graphing calculator, graphically. Number 2 would be numerically or with a table. And then number 3, we're going to do, it's called analytically. Wait, I'm not spelling it right. No, I am spelling it right. Okay. And that's going to be using properties and theorems that we either are going to learn or have learned. So the first approach would be to use something called direct substitution. Direct substitution is exactly what it sounds like. You're going to substitute the number into the equation. So this says here, if the limit of x approaches c of some function f of x, you just do f of c. You plug c in. That's direct substitution. So this says it's important to learn to recognize different types of functions that have this property. And so some basic ones are given right here. These are pretty basic ones that you should be able to recognize. If I'm doing the limit as x approaches some number c, and then my equation is b, there's like no x to plug that in. So the limit is going to just be b. And for number 2, if we have the limit as x approaches c of just x, well, I would plug c in and we would get c. If we've got x to a power, we would plug in c and we would get c to that power. That's what the limit would be. And then for this one, if we have x approaches c and we have a nth root of x, the answer would be the nth root of c, but only if it's odd. If n is even, then c has to be positive. So we just have that extra rule on there where we can only take the even root of a positive number. So the answer would be positive in that case. So these you can all use direct substitution for. And then because of these properties, we have more operations that are going on with the basic properties that we can apply. And I'm not going to read through every single one of these, but I'm going to use addition as an example. It's going to be below, but it says if we have x approaches c of some function plus or minus some other function. So we would put c in for x's in both functions and then add or subtract those together. And then here's another one that says if I've got a function and another function and they are multiplied together, then I could plug c in for each of those functions and then multiply the limits together like that. So this list is available to you so you can start recognizing where you can use direct substitution. But here's an actual example. This part on the right would not be given to you already. I just put that there so it was easier. We don't have to copy it. But the part on the left would be the original question. The limit as x approaches 2. So I'm just looking at each of these. This would be like x to an n, a power. This would be just a linear. And then this one would be a constant. And all of those were in the first list of properties. So I could look at this as being f of x plus g of x minus h of x. So I could find the answer to these three separate things and then add them all up, or add and then subtract the h. So that's what I'm doing. But it's just going to look, and I mean, that's where these three things are coming from. That's really just going to look like I'm literally plugging in for every x. So I'm just plugging in 2 for each x. So we're going to get 4 plus 4 minus 3, which is 5. And that's the answer to the limit of that function. That's direct substitution. Literally plug it in and what do you get? Okay. Should seem like way too easy. Like this is calculus. A limit of a polynomial function, which is what we just did. So you can just kind of shorten what we just did, how we did it separately as 3 separate limits. And we could just shorten that and say, just plug in c for the entire function. Okay. Which is what I was saying. Like the previous properties allow us to plug in each piece and add them together. But this is just saying, you just plug it in the whole thing. Okay. What was it called? It was called I already forgot. Oh, direct substitution. So the direct substitution cannot always be used. It just not always be used immediately. Sometimes we're going to have a c value that if I use f of x, it's equal to a different function g of x for everything except for x cannot equal c. So if the limit of g of x exists as x approaches c, then the limit of f of x also exists. What does that mean? That's something like this guy here. So if I have the limit as x approaches 1, that means I'm going to try my direct substitution, and I'm going to have 1 cubed minus 1 over 1 minus 1. So I get 0 over 0, but that is an undefined answer. Okay, that is an undefined answer. So what if I factored x cubed minus 1, and I did x minus 1 times x squared plus x plus 1. That's a difference of cubes. Then I have x minus 1 on the bottom. What if I factored it? And then we talk about what we did in section 2.6. What could happen after I factor it? Let's cancel. So now I'm looking at the limit of x approaches 1 of x squared plus x plus 1, okay? So this equation here, once those cancel out, x cannot equal 1. That's what they were talking about up here, where they said f of x is totally equal to some other equation where x does not equal that c. That's what we have. So if we find the limit of this second equation, it's going to be the exact same as the limit for the original equation. It's just right at that point where x is 1, what's happening on the graph? A hole, right? So that's why we couldn't find anything originally. But it's going to get closer and closer and closer to that hole. So we'll be able to find our limit once we get rid of the denominator through factoring. So now I'm just going to use direct substitution, 1 squared plus 1, and the answer would be 3. So the hole would be at 1, 3. The graph, the limit as x approaches 1, y is getting closer and closer to 3. So that's the, what's it called? I already forgot. Replacement theorem. The technique for the replacement theorem, what we did is called the cancellation technique. Replacement theorem uses the cancellation technique. So here we go, using the cancellation technique. Right away, I notice if I plug in -3 here, I'm going to have a problem because it's not going to work. So instead, let's see if this factors. It does factor, and the x plus 3s are a common factor, so we can cancel those out. So now I can look at the limit as x approaches -3 of x minus 2. So I direct substitution, do -3 minus 2, and I get -5. So that's the limit. But if I were graphing it, that would be a hole on the graph. When is it that I would get answers like negative and positive infinity? When would that be? What, Christopher? I heard x. Yes, but that's not what I'm talking about. Like if I have x approaching something like -3, when would I get out an answer like an infinity? If there's an asymptote. So how do I know that this is a hole and not an asymptote? Because it canceled in the numerator. If I factored it and it didn't cancel, that's when we start looking to see if we should do like the little big thing where we go like, not little, that's not the little big. That's the one where we do the positive negative stuff, where we like check something just under or check something just above and see which infinity it would be going to. Okay, so evaluating a limit. Can I put in -2? Yes? Because the bottom's fine. Okay. So then we will just do -2 squared plus -2 minus 2 over -2 minus 2. 4 minus 2 minus 2 over -4. So I get 0 over -4, which is 0. So at -2, the y value is 0. Okay. Existence of a limit. I talked about this with the pictures. but we can do it analytically as well. There's only a limit that exists if both left and right sides are equal to that limit. So with the picture, the one that was like had a big break in between, that limit did not exist. So here we have a piecewise function. So we got two pieces. We want to see if the limit does exist. One thing that I noticed, it just has the words. It doesn't have like written with a little limit or anything. But we want x to approach 1. And one thing that stands out to me is, look, that's the part where both are, that's kind of the part where they break. Is x ever going to equal 1? How do you know, Megan? It has to be what, hon? So will it ever equal 1? Will x ever equal 1? So what here is telling me that it'll never equal 1? You're kind of like, what you said was kind of right, but I was looking for you to phrase it slightly different. Barry, do you know what I'm talking about? Well, so I am talking about the less and greater than signs, but there's something missing that makes it, yeah, there's no like equal to. Remember, we would need that to make it actually, so there is a hole here, but is the hole like are they separated or are they connected? So let's find that out. We will find the limit as x approaches 1 from the left. And if we're doing it from the left, which piece will we directly substitute into? The first piece. So 4 minus 1. Now it will never equal, actually, let me write x minus 1, or 4 minus x. It will never equal 1. So this is an approximate what it's getting close to. It will never equal it. But it's getting closer and closer and closer to 3. So we do the same thing for this one. Limit as x approaches 1 from the positive. And anything greater than 1, we're going to use the second equation. So we'll do 4x minus x squared. So we do 4 times 1 minus 1 squared, which is 4 minus 1, which is 3. So if they are the same, then we can say the limit as x approaches 1 of this function is 3. We can say that because both sides are approaching the exact same thing. When we were doing chapter 2, and we had an asymptote, and we had two sides, and one of them looked like this, and the other side looked like this, what was the limit? Let's say that this is 3. As x approaches 3 of this function. What do we have to say for there to be a limit? It has to be what on either side? It's got to be the same. So on either side of this 3, is it the same? One of them's going up and one of them's going down. So what's the limit on the left side? What's the limit as x approaches 3 from the left? Infinity. And what's the limit as x approaches 3 from the right? Negative infinity. Are those the same answer? No. So what would be the limit as x approaches 3? Does not exist. Okay, we use those infinities to graph it, but the actual limit right at 3 does not exist. That's what's new now, is we didn't talk about the limit at 3. We only talked about what the graph was doing on either side. So that's new. Here's another comparing one side. This is a real life application. An overnight delivery service charges $8 for the first pound and $2 for each additional pound. let x represent the weight of a parcel, and let f of x represent the shipping cost. So we're starting at $8 no matter what. Anything under that 1 pound, or does it include 1 pound? Yeah, so including that pound, is going to be $8. Then if we go up, we're going to have to add $2 more. If we go up, we're going to add $2 more in poundage. So we've got a piecewise function, and we also have it graphed already. It says show that the limit of f of x as x approaches 2 does not exist. So how could we justify that the limit does not exist? You want to find the limit from the left and find the limit from the right and show they are not the same answer. So from the left, if x is 1.9 pounds, what would the y value be for 1.9? 10 pounds or $10. If it was 2.1 pounds, just above 2, what would the limit be? 12. Not the same, so the limit does not exist. And I just said because the left and right have different limits. D any is does not exist. Okay, what questions do you have before I tell you something about your assignment? Sam.
So is it the limit doesn't exist because if you have like a one function that sort of won't approach the same value in multiple directions? Is that why it doesn't exist? Because both halves of the function are approaching different things?
Yes, it's because when we do the limit from the two sides, we get a different answer. So we can like look at the graph as well. At 2, well, I can't see my x-axis. At 2, this direction is approaching 10, and this direction is approaching 12. So it's two different places, even though one's open and one's closed. So the limit does not exist if they're going to two different places. I have another equation that is in the book that I didn't put in our notes that is a good example of this as well. But
what kind of question, what's like an example of question that would be asking for negative infinity or infinity for like the limit? Like in what question would you solve that one?
So that was for graphing it.
Oh, and that's only for graphing?
Well, yeah, I mean, we needed to know, we already knew from factoring and looking at our denominator that there was an asymptote at that one place. So we knew the graph wasn't there. We needed to know, was it going up the asymptote or down the asymptote? So we use that for graphing. Okay. Now, let me give you this other example first. I didn't put it in notes originally, and we ended up talking about it in my other class, so I want to talk about it here too. The equation is absolute value 2x over x. I can't remember what we're approaching though. I think it was 0. X approaches 0. Let's find the limit as x approaches 0. So can I go ahead and plug in 0? What happens if I just plug in 0? If I do direct substitution and I plug in 0, what happens? We have a problem. Okay. So let's try to figure this out a different way. Maybe we try the two sides. So let's do the limit as x approaches 0 from the left and the limit as x approaches 0 from the right. Oops. So try something not 0, but to the left. Negative 0.01. What happens when I plug that into the top? I get a positive 0.02. What about when I plug that into the bottom? Negative 0.01. And I'll see if I need to do that or not in a moment. If I plug in 0.01 on top, I'm still going to get a positive 0.02. It's raining. And on the bottom, I'm going to get a positive 0.01. Are these going to be the same answers? I don't even need to finish doing the problem. They're not going to be the same answer. One's going to be negative, one's going to be positive. So not the same answer. So the limit does not exist. So you might not know exactly what you're doing for each of these, and you're going to try some of these different methods that you saw today. Now, one thing that you're going to see towards the end is you might see a problem that looks like, I'll just do it in a different color, the limit as x approaches smiley face of some equation. Let me just make up an equation. X minus 9 over x plus 4. Okay. So you're going to have something that might look like this. I don't know. I'm just making things up, but it's probably not going to have a smiley face in it. But when I go to do this, maybe I'm going to try direct substitution. Will the denominator equal 0 and I'll have a problem with it? No, because smiley face plus 4 is smiley face plus 4. So I'll just have to leave the smiley face in there when I plug it in. And I have no idea about going left or right of smiley face because who knows what that is. So okay, so I didn't go over any examples like that because it's going to have to be it's the very end of your assignment. It's after you've done all this practice. Do you understand it now enough to do things that aren't so obvious? Okay. This assignment shouldn't take too long. We just did a ton of examples in not very much time. So you should be okay on getting through this assignment. Would you guys like me to go over a question from I know not all of you need it, but a question from the application worksheet? Have you started it yet? So better open it up if you haven't started it. I'll open it. I'm just putting it on the same thing of notes. Let me pause the video for a second.